Hello there. In this lesson, we're going to look at the rest of the quantum numbers that we didn't cover in the previous lesson. We started with the shells, which are the layers of electrons around the nucleus, and they were given the symbol N. And then we moved on to these subshells, and these are the different energies of electrons that are possible, and that was given the symbol L. And so in this lesson, we're going to add a little more detail, which includes the different orbitals and the spin. Orbitals are sort of what's illustrated here, where you have different electrons that are of the same energy, but oriented differently. And so we're going to look at how the values are split up for those, and then we'll add the spin component as well. So here is the breakdown from the first lesson. We looked at the first two components, first two quantum numbers, N and L. The second two quantum numbers are the orbital, which are given the symbol M with a subscript L, the scripted L. And then the final one is called electron spin, which is given the symbol M with a subscript S. So M sub L or M sub S for the last two. So orbitals are the way that electrons divvy themselves up within a given subshell. So remember, a subshell is a bunch of electrons that all have the same energy. But orbitals are the pairs of electrons that will have all the same properties in that they will occupy the same amount of, probability space around a nucleus. So to divvy them up, we know that the S subshell only has 2 electrons, and so therefore there's only going to be 1 orbital there. So we got 2 electrons making 1 orbital. The P subshell has 6 electrons, and so basically just divide by 2 and you get the number of orbitals, so that's 3 orbitals. The D subshell has 10, and so therefore 5 orbitals, and F has 14, and therefore 7 orbitals. So the orbitals are the possible pairs of electrons that you can have in a given subshell. The numbers they give to these orbitals for this M subscript L value go from negative, whatever the value for L is, to positive L. So for the 0 is just the 1 orbital, and so it'll have the value of 0. For the 3 orbitals of the p orbital, you start at negative 1, and then 0 and plus 1, right? So that'd be 3 orbitals for the p subshell. And D is going to start at negative 2, and then go to negative 1, and 0, and plus 1, and plus 2. And then same thing for the F. You're going to start at negative 3, and then negative 2, and then negative 1, and 0, plus 1, plus 2, and plus 3. And you can think of these as ways in which you can label the different orbitals within the same subshell. Okay, so if you recall, all the electrons in a given subshell all have the same amount of energy. So energy isn't the distinguishing feature for orbitals. What it is orientation. It's the way in which these orbitals are relative to each other in space around the nucleus. So put a nucleus in the center of these Cartesian axis. If you put one on the x-axis here, so there, if you recall that the p subshell had this double lobed shape. So that'd be 1 orbital of the p subshell, and that's on the x-axis here, right? So that'd be p with a little x. The second orbital can't be in that same space, and so it'll go on a different orientation relative to where that first p orbital was found. And so up and down, and that'd be p on the y-axis. And then the third orbital for p could go on the z-axis, which would be like in and out of the screen, which is kind of hard to represent here. But you can kind of think of it as like a little jack. If you ever played jacks before, the little jacks that have the lines oriented in all 3 directions. And so each one of them would be a different orbital, same energy, just oriented so they don't overlap with each other in space. The last quantum number refers to the property of electrons that gives them, and also the atoms that they're a part of, magnetism. So this is sometimes called the magnetic quantum number, m sub s. And in order to explain that property, they use the analogy of like a spinning top. And so if the charge of the electron is spinning in one direction, you will get a north and a south pole that'll be the opposite of one that spins in the opposite direction. And so the only way in which two electrons can exist within the same orbital is if they have opposite magnetic properties. So they call that opposite spin, and the values they give for that are +0.5 and -0.5 in order to distinguish one from another. So only two electrons possible per orbital, and only if they have opposite spin qualities. So in order to include those other two quantum numbers in the representation of electrons around an atom, we can use what's called an orbital box diagram or a line diagram that distinguishes the different electrons by orbital. And so there's a couple patterns that you have to learn to follow. What you're going to do is you're going to use the lines to represent orbitals. So the little lines here, or you can use boxes, doesn't matter. These represent orbitals. And so S only has the one orbital. P has 3 orbitals, right? So you have 3 boxes. And these would have 5 and so forth, right? You can use the boxes or you can use the lines. Either way is fine. And then one pattern that electrons follow for the most part is called Hund's rule. And Hund's rule is just a way of filling the orbitals within the same subshell. So you're going to still start at the lowest energy subshell and work your way up, just like we did with our electron configuration. But when you're filling up a bunch of orbitals within the same subshell, what you want to do is spread out the electrons as much as possible. So what that means is that we're going to have 2 electrons in here. We're going to use arrows to represent the spin values. The up arrow we could say is the +1/2, and the down arrow is -1/2. And then what is that? We have 7 electrons for nitrogen. We've used up 4, so you go 5, 6, 7. So that would be following Hund's rule, is spreading out the electrons into the different orbitals before doubling them up. So that would be correct. The incorrect way to do that would be to do 1, 2, 3 like that. That would be not following Hund's rule because you didn't spread these out before doubling them up. So yeah, if you can follow that pattern, then you'll have yourself a nice representation of all the electrons with their 4 quantum number properties. Alrighty, let's try a few. So oxygen has 8, so that'd be 1s2, and then 2s2, and then 2p4. There we go. And so for S, you're going to have 1 box. So you put a box down. I like boxes. If you want, you can just use the lines. And then 3 boxes for the P. And maybe use a different color here. We'll fill them in. Electrons spin up, spin down, spin up, spin down. Just by convention, tend to put the up arrows in there first. So 1, 2, 3, and then we double up for the 4th one. Great. Nickel, it's much larger here. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d8. Okay, so put a whole bunch of boxes in here. So box for S, 3 boxes for P, box for S, 3 boxes for P, box for S, and 5 boxes for D. And they get bigger. 1, 2, 3, 4, 5. Great. Now we'll fill this in. Up arrow first, then down, up, then down, up, 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 down, down, down. Not that it matters when it's full. Up, then down, up, 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 down, 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 up, down. And here's where it matters. 1, 2, 3, 4, 5, 6, 7, 8. There you go, orbital box diagrams for oxygen and nickel. All right, now one other way that you might see electrons in their orbitals represented is with an energy level diagram. And so instead of having a horizontal representation of increasing energy, this one's vertical. And it works the same way. You just show the overlap of the subshells and their energies in a vertical manner. And I find a little trick here. I prefer orbital box diagrams to be horizontal, but you'll still see this sometimes, so I thought I'd share it. So if you want to put 26 electrons here, you just start from the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and 26. So there you go, energy level diagram, pretty much the same way, just bottom to top rather than left to right. Okay, hope that helped. See you soon.